Again, I'd like to welcome everybody to this researcher engagement meeting hosted by the SimCenter. My name is Greg Deierlein. I'm on the faculty at Stanford University and also co-director of the SimCenter. This morning, this particular researcher meeting, we're going to be looking at regional earthquake impacts on buildings, recent and emerging applications. Now, before I get to introducing a few more details about today's session, I just want to say a couple of things about the SimCenter and ways that the research community can engage with us. We have a number of the meetings, such as we're having today. So this is the first one on the 13th. We have three more that are scheduled. You can see on the topic shown here, looking at hydrodynamics, looking at wave forces, one on wind engineering, and then disaster risk analysis. That's a little bit more looking at regional effects. We'll also have a number of subsequent ones being announced in the new year. So watch for announcements on those different topics. Also, this spring, we're going to repeat the NHERI Computational Symposium. So many of you may have participated in those previously. We've had three successful ones, so we're going to repeat that this May 27th, 29th. Watch for, there'll be a call for abstracts to participate in that symposium. That call will probably go out next week. And this year it's going to be held on the UC Berkeley campus. And finally, another way to kind of reach out with us is to engage in office hours with our SimCenter staff. So if you go to the SimCenter website, you'll kind of see places where you can sign up to basically go to office hours with staff. So if you're using our tools and have questions on any or want to look at extending certain features of it, it's a great opportunity to interact with staff directly. So in terms of how to stay involved, our website is the best source. And if you go, there's a button there called SimCenter Community. And if you go click down into that, you'll get to these menu items there. You could, if you're not already subscribed to our newsletter, you could subscribe to that so you're updated on all the information. We have working groups. Also, if you're working on code development, the GitHub discussion is a good and/or using our tools. That's kind of our forum, if you will, for question and answer. And of course, the meetings, the researcher engagement meetings that we're holding today. So those are general things about engaging with the SimCenter. So in terms of today, looking at the regional effects of earthquakes, the key purpose of this is really to foster engagement with you, the research community, by sharing some latest developments, experience, and successes, and so forth on implementing regional earthquake simulations. I'm going to give just a couple of slides, and I'm going to turn it over to Adam Zarnowski, who's our Associate Director for Research Outreach, who'll give a quick overview of some of our tools that relate to seismic risk assessment. And then Carlos Molina-Hutt, Associate Professor at University of British Columbia, will share some of his experiences on applying these tools to individual buildings and then incorporating those in regional simulations. And Carlos is not so much going to focus on the conclusions, the findings from his research, but rather focus on a little bit what's involved with kind of putting these computational workflows together. So that's really the main point today. It's not so much to show results, but to share experiences on using these computational tools, where successes have been, where some of the challenges are. Now, the vision in the SimCenter, I think many of us would share, is the idea that we want to do high-resolution regional simulations. This is moving beyond the capabilities, say, that are available in a program like HASIS, which has been available for over 20 years now. But through these high-resolution and high-fidelity models in them, to really start to look at local issues and really to help cities, go beyond engineering buildings to engineering cities, to help cities inform some of their risk mitigation plans, retrofit programs of all sorts. Could be, today we'll focus on buildings, but equally to lifelines and transportation systems. Finally, I'd like to point out that throughout the SimCenter's development, our focus has been on putting computational tools together, and in particular, thinking of connecting modules into computational workflows. And from the start, we've kind of embraced the peer performance-based framework for that. But we've been extending it. And so earlier this year, there was a paper published. You could see the title up there and a few more details in the Frontiers of the Built Environment, where we kind of explain in more detail the extension of the performance-based framework. And for those of you that have seen this before, these boxes are very familiar. It's a modular way of looking at characterizing different components of doing an earthquake, a performance-based earthquake analysis of one building or of an inventory of buildings or of a region, from characterizing hazard to the output. But where we've been building on this is really looking more carefully at, for regional simulations, at how you develop information on the inventory of buildings and the population of people in those buildings, and carrying that through these computational simulations into looking at what's the outcome, what are the consequences, but going beyond just the damage and losses to start to look at the recovery analysis. And of course, that's a key part of so-called resilience. And the other part of this, you'll notice that there's multiple kind of arrows and ways kind of through this process, thinking, mixing and matching lower and high fidelity models, also to characterize the uncertainty in not only a specific building or in the hazard, but also in the population of buildings, correlations between buildings. So that's a key feature that we've been trying to emphasize in the computational workflow tools. Okay, so that's a general introduction. So I'm going to turn it over now to Adam Zarnowski, who will give you, as I mentioned, a bit more detail on some of our tools. Oh, and
Thank you, Greg.
by the way, while Adam is pulling up his slides, let me point out that what we'd like to do is hold questions till after Adam's talk and Carlos's talk. But also, we'd ask you to, there's both a Q&A button and there's also a chat. Maybe if you try using the Q&A, but either one of those, if questions come up or you have thoughts during the presentations, please write them in there. Because really, once they get through the goal of their presentations is to kind of motivate discussion. We'd like to hear your questions based on what you've heard, but also if you have experiences that you'd like to share or observations with tools, we'd likewise like to hear that. Okay, so Adam, turn it over to you.
Thank you. Do the slides look okay?
Yeah, we
You
can
see
see
them?
them. Yep.
Okay. Okay. Hi, everyone. So I will spend about 10-15 minutes to give you a quick overview of the tools that we have for seismic risk assessment. I will not go deeper into either of the tools, and I encourage you to reach out if you are not yet familiar with them and you would like to know more, or you can look at our website to learn more. I will have some links in the slides that can help you find that information. I will start where Greg finished his slides. So we have this conceptual framework that we developed by extending the peer framework that was for mainly what we call local analysis. So single buildings, we went to regional and multi-hazard types of studies conceptually. And then we also worked quite a bit on software implementing this framework in various tools. What I want to emphasize here is that we do have a backend which is written in Python and C++, and it is the engine that runs these simulations. It is the same backend behind all of our applications, and we have several front-end or user interface or desktop applications that are making it easier for researchers and practitioners to use the backend and leverage that engine for their work. And we tailor these front ends to different use cases and make it fit different user types. And I will talk about a couple of desktop applications today that are related to seismic risk assessment. Another important thing that we for our work is to serve different levels of user involvement, I would say. So when you use our tools, you need to go all the way from setting up the environment to running some analysis and then processing the results. And we think about this as a matrix where you can either be looking for something like a superficial involvement where you run a streamlined analysis, you don't want to get deeper into the code, you don't want to change anything, you just want it to work, or you want to do some contributions perhaps in some parts and you want to go much deeper. So you are looking for something that is flexible, where you can change things, where you can bring your own models or your own ideas, your own methods, and you can go into the code and edit how it works. And we want to support both of those cases. And we want to support you to go deep where you want to go deep, but keep it superficial where it is more convenient to be superficial. As you can see, we have different solutions for each step of this journey. and allow you to pick your own level of depth at each step and move between them. I am happy to talk about to any of you about this and how it can help you in your work. If you sign up for office hours, for example, that's a good opportunity. We have half an hour and we can discuss which kind of approach could work best for you. Now about our applications. We have 8 different tools that we usually highlight. 6 of these are desktop applications, and 2 of them, the ones in the bottom right corner, are what we call packages or software tools, which are not with a user interface. They are standalone applications that are also part of our calculation engine. And I will highlight the ones from these that are related to seismic risk. So I'm not going to talk about the wind and water kind of tools. The first one, we start with structural response simulation. This is earthquake engineering with UQ, EEUQ in short. This application focuses on running structural response assessments, either time history simulations or other surrogate model-based simulations. The feature that is most popular in this tool is our ground motion record selection tool within it module, where we use the peer NGA database, and we are selecting ground motions from there to match a target spectrum that you provide. Another thing that is new in this application is the domain reduction method that we built in that allows you to do more advanced soil structure interaction kind of studies and connect with physics-based ground motion simulation results. After structural response, the next step is damage and loss simulation. This is where our first tool comes in that is not a desktop application. This is called Pelicun. Pelicun is an engine that we developed specifically for damage and loss simulation. It follows the same kind of mindset that we have for all of our tools and our bigger framework. It's modular, it's flexible. You can do many kinds of damage and loss simulation in it. One of the most popular things that is used for is FEMA P58 style simulations, if you are familiar with that high resolution method. But it is also working for hazardous kind of earthquake simulations that are more regional scale and building level in resolution. One thing that is interesting about Pelicun lately is that we are introducing regional and multi-building assessments in it. It was originally designed for a single building assessment, and now it can run at least hazardous earthquake assessments at a regional scale, which is very fast and allows you to run tens of thousands of buildings in your laptop in a matter of minutes. So this is what we are excited about, and we want to expand this to other types of hazards and other types of methods. So eventually it will support either a single building or multiple buildings with the same tool. If you want a desktop interface around damage and loss assessment, then PBE is the tool that you are after. PBE wraps around Pelicun and connects to EEUQ that I just mentioned. So you can use EEUQ to run a structural response simulation, and then the results are automatically passed to Pelicun. And from there, you can go on and even look at functional recovery simulation. Currently, we have Ready from ERA built into the tool, so you can run a Ready simulation while not leaving PBE. And we are working with Carlos and his group now to also bring ATC 138 and threads. Those are 2 other methods for functional recovery simulation into PBE. These 2 methods already work with Pelicun, so if you want to start working with them, you can. But that means you manually have to pass the data between the tools, and soon they will be available in PBE to allow benchmarking and comparing those different functional recovery simulation methods. One thing that I forgot to mention when I was talking about Pelicun, and it still applies for PBE, is that we also have this damage and loss model library, where we are collecting fragility functions, consequence functions, and loss functions, and we are making them publicly available. And we are encouraging everyone who has their own functions that they would like others to use to contribute them to this repository, because then they are easy to use in Pelicun and PBE, and probably they will be used by more people, and as they are becoming more accessible and discoverable. PBE is still a single building focused tool. If you want to look at a regional scale analysis, then the next step is going to R2D. R2D goes all the way from defining the hazard events to the recovery of the region after a hazard event. It is not only earthquake focused, it supports multiple different hazards. So you can look at earthquakes or wind type of hazards or water hazards. And it supports and aims to facilitate analysis on not only buildings, but also on infrastructure type of assets. It is not only for high resolution simulation that you would imagine in a seismic context, say open seas type of simulations. We also support running simulations that focus only on fragility curves and driving them with intensity measures. So you don't need to do a structural response simulation, and also interested in surrogate models and using those for these analysis. There are two features in R2D that I would like to highlight that are popular and I believe allows you to do interesting research and saves you time. One of them is the earthquake scenario simulation tool that is available as an extra tool within R2D. This allows you to generate earthquake intensity measures for a particular area. Here is an example where you pick a couple of grid points in the area and then find the relevant seismic sources around it. You can pick a particular source, or you can use all the sources if you want a PSHA kind of analysis. You can choose what kind of ground motion models you want to use. You can look at ground failure if you want to. You can consider spatial correlation models for the intensity measures. And in the end, if you want to, you can even do ground motion record selection. So if you want to run, say, an open seas kind of analysis or any kind of nonlinear time history analysis, you can pick ground motions that match the intensity measures for each grid point, and that way enable that kind of high fidelity analysis at a regional scale. This is all in a desktop application in a convenient user interface, so it makes your life much easier, and you can export the results. So even if you don't want to work with R2D after, you can use only this tool to generate your ground motion inputs for your study. Okay, the other thing that is important for regional simulations that I want to highlight is inventories, mainly building inventories or asset inventories that you need to be able to drive those analysis. We are helping the community by having a tool that is specifically focused on streamlining inventory generation. We identified a couple of steps that are involved in these, including collecting data and then using potentially images and computer vision to identify other kinds of features, then merging all of these different data sources in a thoughtful way, and plugging or filling the gaps in the data, which are, in our experience, almost inevitable. One interesting feature in BRAILS that is coming in the next month is to not only focus on assets, but also include people. And we will have households assigned to buildings automatically within the United States. We will talk about this on December 4th in one of the upcoming engagement meetings. So if you are interested in that, I encourage you to register for that meeting. And finally, after you have a hazard event, you have an earthquake, we are interested in what will happen, how will the communities recover. This is also something that we are able to simulate. We are collaborating with Nikola Blagojevich, who is the developer of PyRecodes, which is a general tool for recovery simulation. And we have already integrated PyRecodes into the SimCenter ecosystem and passing the damage and loss results from R2D to PyRecodes, and then connecting to different tools that are able to do water network simulation and traffic simulation, so that we are able to consider interdependencies between these different networks and how they also relate to the communities and the buildings in the area. We have a couple of examples showing how PyRecodes can do these, and I encourage you to check out those in R2D, and also to reach out to Nicola or look at PyRecodes to see the potential in that tool. Now, as a last thing, I would like to mention to finish and go full circle with this context, we are developing test beds that are repositories of data and examples that focus on a certain area. And the idea is that we would like to support and foster benchmarking different models, different ideas by providing the necessary inputs and then allowing you all to check how your model, how your idea compares to running a different idea in the same area. We are choosing areas that are rich in data and where the local stakeholders are interested in what the outcomes of such analysis could be. And one particular area that we have for earthquake-related studies is the San Francisco Bay Area. We've been looking at this area for a couple of years now, and we have collected interesting and, in our opinion, useful data sources and metadata about this area, which includes building inventories, event intensity measure fields, as you can see on the slide. We have been pulling in locally appropriate models of buildings. There are certain kinds of design choices that were made in that area that are interesting because we want to know better how they would perform in an earthquake, and we are collecting high fidelity finite element models for those. And we also want to see reports and relevant studies in that repository so that people can get up to speed on what is interesting to look at and what has been done in the area. The San Francisco testbed is one place where we can have such benchmarking done. If you are interested in working in another place, I believe that this kind of data organization that we do in the San Francisco Bay Area could be applied in other places, and eventually we could have a multiple test beds like LA or Seattle or other places that are equally interesting and could engage the research community and lead to collaborative work on understanding our models better. My last slide is about how to connect with us. Greg already mentioned a couple of options. I only want to highlight here the office hours again. You can see that you can connect to either of us, Matt Shuttler, who's on the call, Frank, who's also on the call, and myself. You can see when we are available. It's really easy to book a 30-minute appointment. This is a low-key thing. You don't need to be a professor to do it. So if you're a student and you are interested in learning more about our tools, please go ahead and book an appointment, and we would be very happy to talk to you. And with that, I would like to give it back to Greg or pass it to Carlos. Thank you.
Okay, thanks, Adam. Yeah, so pass it to Carlos. And Carlos, while you're pulling up your slides, want to thank Adam for that. And again, encourage folks, if you have kind of questions or comments, you could put those in the chat, be thinking of them. I would like to mention, I was looking through the list of participants, as Matt pointed out, Nikola Blajovic, who developed the Pyre codes for recovery that we're kind of building in, is actually on the call today. I noticed a couple of our SimCenter staff who've graduated, Sangri Yi, who's at Rice University, and Jinyao Zhao down at Caltech. They worked on Sangri, some of the surrogate modeling, and also some of the UQ kind of propagation in the tools and some of the imputation for inventory data. Jinyao worked on R2D and some of the hazard functionality that was described. Also a number of faculty, my colleague Jack Baker and also Henry Burton, who've contributed parts of their codes and models, because indeed a key part of what this is all about is getting the community together and really sharing models and sharing data, recognizing as a community we could tackle bigger problems that way. And also as a researcher, I mean, that brings more awareness of the research that you as a researcher has done. So it's apart from publishing papers, I think to see other people using your tools is really tremendous. So Carlos, turn it over to you.
Thank you very much. Can you confirm that you can see my screen in presentation mode and you can hear me?
Yep.
Okay. Yeah. Yep. Excellent. Thank you. Well, good morning, everyone, and thank you for joining us today. I think I know most, but maybe not everyone on the call. So for those that I haven't met, my name is Carlos Molina Hutt, and I'm an associate professor of structural and earthquake engineering at the University of British Columbia, where I lead the Engineering for Seismic Resilience lab, and you have a link to our website there in the slide. I've titled my part of the presentation Advancing Functional Recovery and Regional Seismic Risk Assessments through Integrated Simulation Tools, to build on some of what you've already heard today. So Greg started us off with an overview of the session, simulation of regional earthquake impacts on buildings. And then Adam provided an overview of relevant SimCenter tools, highlighting, the resources and capabilities that are available for seismic risk modeling. And now I'll spend a little bit of time illustrating how these different software components can be applied and also how they interoperate to support more comprehensive analysis using examples from my research group. And we hope that this will set the stage for a productive discussion session after my presentation, where hopefully you can share some of your own experiences and insights with regional simulation and the tools that you've been using. So here's a quick overview of what I want to be covering in my part of the presentation. I'll touch on three main research areas. So first, I'll talk about developing a new performance metric for individual buildings. Second, I'll talk about building an automated workflow for portfolio scale analysis. And then the third topic will be on enhancing the fidelity of regional seismic risk assessments. And these topics build in scale. The first one focuses on individual buildings. The second one expands from individual buildings to a portfolio. And then the third one takes an even broader view, just looking at regional seismic risk assessments generally. After the three research topics, I'll also share a few words about how these tools can be used in teaching. And what I want to do to sort of have a little bit of consistency is for each of these, I'll go through the motivation behind the work. I'll then highlight the SimCenter tools and other related tools that can also be used, at least in the projects that I'll be showcasing. And then I'll talk a little bit about what worked and what didn't work, and I'll call that the 3WD. And finally, I'll point to a few related studies that connect to the different topics that I'll be sharing with you. And just to note, as Greg pointed out, I'm not going to be talking about the results of our research studies here today. The focus is really on the process that we followed, the tools, and also the lessons that we learned along the way. And if you're interested in the results of the studies, what I'll do is I'll provide links to the different papers that have all the details for those. Okay, so let's start with the first topic. It focuses on developing a new performance metric for individual buildings. And the goal here was to develop a standardized framework to quantify how long it takes a building to reach different recovery states after an earthquake. And this effort led to the creation of a tool that we call TREDS, or Tool for Recovery Estimation and Downtime Simulation, that Adam also made reference to in his slides. So since the release of the THEMA P58 framework in 2012, which was then followed by the READY guidelines in 2013, I participated in several studies with Greg's and some others on the call, assessing post-earthquake downtime in buildings. And each study kind of approached recovery slightly differently, building on what we had learned from the previous one. So with TREDS, our aim was to bring consistency and transparency to how we were assessing recovery time. And the timing of the study was actually quite fortunate, because our framework was sort of published at the same time, or within the same time frame as other similar frameworks. Like Vesna Tursik has a framework called FREC. Dustin Cook also published a framework with Abby, Lyle, and others, which was later adopted by ATC 138. And all of these, came out actually within a few months of each other. So it was interesting that a lot of folks were thinking about this. So all three frameworks share a common foundation. They integrate component level damage with probabilistic models of repair duration and impeding factor delays. And more specifically, TREDS generates recovery trajectories for a range of recovery states, such as stability, shelter in place, or functional recovery, as you can see in the image on the slide here. And as I mentioned earlier, for reference, if you want to learn a little bit more about this, we have an earthquake spectra paper, and you can see the DOI in the bottom right of the slide. So this diagram illustrates how our framework builds on Pelicun's implementation of FEMA P58. The light green cells represent components involved in the FEMA P58 framework as implemented in Pelicun. And then the cells in purple correspond to our TREDS analysis. So beyond the standard FEMA P58 assessment, our approach introduces a couple things. So first is the quantification of the immediate post-earthquake usability of the building, and this is determined by looking at the severity of damage across key building components. And then the other one is the modeling of temporal recovery, so capturing how a building progresses towards achieving a certain recovery state while accounting, of course, for the repairs that are necessary to reach that state, and then factors that may delay the initiation of those repairs. And together, these enhancements enable a way of describing building performance using resilience-based metrics such as robustness or rapidity that we often found in the literature, but specific to the performance of the building. For example, if we were to do a multiple stripe analysis of a building, we can then evaluate the robustness by examining the building's performance immediately after the earthquake, so before there are any repair activities. And for illustration, the figure in the top right shows the percentage of realizations in which the immediate post-earthquake usability or condition of the building fails to meet a specific target across different return periods. And in this case, the target recovery state corresponds to shelter in place. And we can see, for instance, that at the 475-year intensity level, for example, there's a 22% probability that damage will hinder achieving that recovery state. So this is a way to describe the behavior of the building in terms of its robustness. We could also evaluate the rapidity or the time that it would take to return to a recovery state, and we can describe the probability of downtime to the recovery state in question exceeding a predefined target. And the figure in the top right shows the percentage of realizations where downtime to functional recovery in this case surpasses a predefined threshold across, again, intensity levels if you're doing a multiple stripe analysis. And in this case, for instance, we could look at the 475-year intensity level again, and here we would see that there's an 88% probability that downtime to functional recovery would exceed 4 months. So those are some examples of the types of metrics that you can generate using TREDS. Now, in terms of what worked and what didn't, I think one of the main challenges was obtaining all the relevant input variables directly from Pelicun outputs, which we needed for our framework to be executed. And for this, we actually had to work with Adam to ensure that Pelicun could provide some intermediate calculation results, which weren't originally reported. And this is something that Adam was quite happy to do, and I believe now it's just standardized within the framework. In terms of something that was a bit more challenging, and this is probably more on me and my research group, is keeping our framework regularly updated. And Adam was already working on a release, right, or a good update to the framework. So, well, we haven't actually, we've done most of the work to update our framework to be consistent with the latest version of Pelicun. We have not yet released that, and that's something that we're hoping to do, as Adam mentioned, for integration with the PBE tool in the coming months. Now, I also wanted to briefly talk about related studies, right? Or what else is there associated with this? And once our framework was published, many students were quite eager to use it for other applications. So for instance, my former student, Kristen Blows, I think she's on the call, used it to outline the details of what it would be to conduct a risk-targeted evaluation of functional recovery performance, mirroring a lot of the calculations that we would do, for instance, to evaluate the annualized collapse risk. Another student, Poria Kurpas, he used it to conduct a variance-based sensitivity analysis to understand the impact of parameter selection on both loss and recovery time estimates, because there are a lot of variables that we need to select and assign them a value. And this is actually a paper that we co-authored with Adam. And again, the DOIs for these papers, Kristen's is in earthquake engineering and structural dynamic, and Poria's is in earthquake spectra, are in the bottom right of the slide if you're interested in learning a little bit more. Okay, so for the second topic, I wanted to focus on developing an automated workflow to streamline the assessment of tall, non-ductile reinforced concrete shear wall buildings, which are a common yet quite seismically vulnerable type of building within Vancouver's building stock. In particular, these are what we refer to as pre-1980s buildings. So the framework brings together data collection, machine learning-based archetype generation, and automated seismic performance assessment into a single and reproducible process for portfolio scale evaluation. And in this study, we concentrated on non-ductile reinforced concrete shear wall buildings that emerged during a boom in construction after 1956. And this essentially followed a change in the zoning laws that effectively permitted taller structures. And you have a news clipping there that talks a little bit about this change in the zoning laws. And what you can see here are photos of Vancouver's West End neighborhood, where many of these buildings are located. I'll go back real quick. So on the left, you can see the neighborhood before 1956. And then on the right, you can see it after, in particular 1969. So just a few years later, and you can see the significant development, right, of tall buildings in this neighborhood. Now, because of the rapid development of these buildings, it happened before we introduced ductility requirements into the Canadian Code, which happened in 1984, and before there were many significant revisions to our seismic hazard estimates. Those are reasons why these older tall buildings are really a bit of a concern, and they weren't closer evaluation. So those were the focus of our study. So an interesting aspect of this is that we had access to a detailed inventory of roughly 350 tall non-ductile reinforced concrete shear wall buildings that were compiled by some of my colleagues at
Carlos, if you can hear me, I think you've frozen. Maybe we'll give you a minute to come back.
Yeah.
Okay, yep. So you had just said some of your colleagues from, and we didn't hear the rest.
Oh, okay. Sorry. Yeah, I didn't even get the warning of unstable connection. So please interrupt me if that happens again. You can still see my screen, okay?
Yeah, we see it. Yeah.
Okay, great. So I was mentioning that a neat aspect of the study is that we had access to detailed inventory of roughly 350 buildings of these non-ductile reinforced concrete shear wall type that were compiled by my colleagues at UBC. And the data set includes all buildings that are 7 or more stories built before 1980. And it contains general information like you would expect in a typical exposure data set. So, we have the address, the year of construction, the occupancy, the number of stories, the floor area. But then we also had more detailed structural data for each individual shear wall within each building. And this included, the dimensions of the wall, the location on the plan, the orientation, the tributary area, and even reinforcement details. So by leveraging this database, we were able to automate the generation of archetype reinforced concrete shear wall buildings for use in our study. And we took this approach because we didn't have permission to model individual buildings, and also because many similar structures exist beyond the West End neighborhood where we have all this data. And this presented, as we saw it, an opportunity to augment the existing inventory and generate detailed 3D numerical models for all non-ductile reinforced concrete buildings identified within our regional exposure data set, which you see a subset of it on the left, filtered by construction era. So this was a way to then extend everything that we had data for in one part of the region to then the region more broadly. So to generate these archetypes, the user needs to provide 2 input variables, which are typically encountered in an exposure data set. So the number of stories and the construction year, to ensure it's of the type that we're looking at. This is, of course, only for reinforced concrete shear wall structures. And then we use the UBC inventory to develop plausible archetypes by a random forest regression model. So the workflow for this process is shown on the diagram on the right, and it has 4 key steps. So first is to determine the dimensions and aspect ratio of the floor plate. The second is the shear wall areas in the X and the Y directions of the building. Then we determine the number of planar walls in each direction, and also wall assemblies that we might encounter. And then the fourth step is to sort of determine the overall distribution of these walls, which in past studies that my colleagues carried out, they sort of broadly categorize into W1, W2, and W3, depending on the typical arrangement of the walls. And I must admit that what's unique about these buildings is that they're all quite different. So it was quite an undertaking by my colleagues to sort of go through all this data and try to make sense out of typical patterns. Then the final step that we also included was checking that the archetypes that we generated actually met the building code requirements of the time to ensure that that was an archetype that we could use in the study. And this work was led by Prateej Kakoti. I think he's on the call, even though it's super early in New Zealand. He's a postdoc with Ken Elwood right now, and soon to begin a Marie Curie Fellowship at University College London with Carmine Galasso. And his most recent paper goes over all the details of this framework. It was accepted in the Journal of Structural Engineering. And yeah, I refer you to that if you want to learn a little bit more. I've included the DOI, which is in the bottom right of the slide. We've actually been assigned a DOI, but it doesn't work yet because we just submitted the final page proof corrections. But I wanted to make that available in case you wanted to go over those details. Hopefully, it'll be up in the next few days. Okay, so the archetypes buildings that I talked about were then feeding directly into the computational pipeline that I'm showing on the slide. So here for the hazard characterization, we actually use physics-based ground motion simulations of magnitude 9 cascading subduction zone earthquakes that were developed by the M9 team at the University of Washington in partnership with the USGS. And then the archetypes were generating using the model that I described in the previous slide. So the benefit here, I guess, linking back to a lot of what Adam was talking earlier, is that we could then use this information to conduct our structural analysis using OpenSeaSpy, and then the building performance models in Pelicun, and then the recovery models in TREDS, which I also described earlier in the first topic. And this integrated framework really, enabled us to calculate lots of interesting metrics, right? So we could look at the collapse risk, we could look at the economic loss, and we could look at recovery metrics in these buildings. And I think the key emphasis here is on the scalability and transparency of the workflow, which really lays the ground for doing this at a more regional scale implementation and integrating SimCenter tools along the way. So in terms of what worked and what didn't, I think one of the key successes in this work that Prateej did was really achieving the seamless assessment framework and being able to leverage SimCenter tools effectively throughout different steps of the calculation. I think a slight issue, because we tried to do this initially in our 2D, were some inefficiencies in the calculation, in particular if we want to use complex OpenSeaSpy models. But I think some of these issues have already been addressed, and we can talk a little bit more about this in the Q&A session. I think in terms of the downsides, I think there were really missed opportunities. In particular, as I later learned about BRAILS and EUQ, which I think we're still interested in exploring on one side to really improve the archetype generation and hopefully be able to expand that. And then on another side, evaluating the sensitivity of some of our modeling assumptions, because as you can imagine, there's a lot of modeling parameters that need to be selected, and in particular, I'd be curious to use EUQ to look at how collapse risk would vary if we change, modeling parameters in terms of our 3D models of these non-ductile reinforced concrete shear wall buildings. Now, as for related studies, Poria Corpas, who I mentioned earlier, applied similar concepts to improve recovery time consequence models within regional risk assessments. So he demonstrated this approach using a portfolio of, in this case, modern reinforced concrete shear wall buildings across the Metro Vancouver region, leveraging, again, a lot of the work that was done in TREDS. And the DOI for this paper is listed in the bottom right if you're interested in learning more. And I'm really trying to talk about these related studies is because I think a lot of it kind of builds on each other. So once you start playing with a lot of these tools, there's really opportunities to do so much, right? The sky's the limit, really, once you start tapping into these resources. Okay, for the final topic, I would like to briefly discuss some of the challenges that we face in conducting regional seismic risk assessments, in particular here in BC, but I think these challenges apply to other regions as well. So in Canada, we're very fortunate to have access to a national seismic risk model, which was developed by Natural Resources Canada, or NRCan, which is essentially the equivalent of the USGS. And they did this in partnership with GEM. So having access to a model like this at a national scale is really quite remarkable. And it's starting, to get momentum, and it's being used by municipalities like the City of Vancouver or the City of Burnaby to support risk-informed decision making. However, in my view, there are significant limitations to the model, and often these are not well understood by the decision makers. And I wanted to provide some examples of this. So this is a satellite image of the Metro Vancouver region. So we're in Western Canada, just north of the US border. And this is one of the most, populous regions in the country. So Metro Vancouver has roughly 3 million people, and it's a collection of 21 municipalities, which of course includes the city of Vancouver, and it's where UBC is located. And the region has a high concentration of tall buildings, which are sensitive to long period ground motions. Now we're exposed to a range of seismic sources, including the Cascadia subduction zone, which can produce magnitude 9 earthquakes and dominates the hazard at long periods, and therefore that's of significance to these tall buildings. Now, in addition to this, the region lies essentially above the Georgia Sedimentary Basin, which can amplify ground motions, in particular at long periods. And kind of linking back to our National Seismic Risk Model, unfortunately, that model only really represents tall buildings in a very simplified way, using fragility functions that were derived from single degree of freedom system models. And it also doesn't account for the amplification effects of deep sedimentary basins like the Georgia Basin, or at least this is something that's not included within our National Seismic Hazard Model that feeds into the National Seismic Risk Model. So I think if you're interested in exploring some of these issues, the SimCenter's R2D tool, or broadly speaking, RWHALE, the regional workflow for hazard and loss estimation, is really well suited for exploring these problems and thinking about ways of enhancing the accuracy of our simulations. So when studying the regional impacts of an earthquake scenario, the goal is ultimately to come up with a series of risk metrics, right, that can be used for decision making. And typically, this is done using ground motion models that you can then leverage to develop shake maps, and then you use these as inputs to a building class and asset level set of fragility and vulnerability functions that together give you the risk metrics of interest, right? And this is very much the framework that Canada's National Seismic Risk Model follows. However, as I discussed in the earlier topic, there might be certain types of buildings that you want to look at more closely, or that maybe aren't captured well in this sort of generic type of regional seismic risk assessment. So we could take advantage of things like physics-based ground motion simulations, which we can then leverage in terms of their time history analysis to use as inputs to detailed nonlinear time history analysis models. And then we could evaluate the impacts to these buildings at a higher resolution using tools like Pelicun or TREDS, which rely on component level analyses, as opposed to these, building level functions that we would use in conventional regional seismic risk assessments. And you could argue we can even take a little bit of a hybrid approach here, where maybe we still want to leverage the physics-based ground motion simulations because they capture Bayesian amplification, but then we're happy to effectively follow that kind of conventional path where we then generate shake maps and then follow the approach that you can see on the left-hand side of the diagram on the slide. So depending on our path of choice here, what effectively happens is that if we use different paths for different types of buildings, we can end up with what I'm calling a multi-fidelity regional seismic risk assessment, right? So we might have some buildings that we're assessing at a low fidelity, or maybe a hybrid fidelity, and then others that we're potentially assessing with higher fidelity. And of course, depending on where we intervene, we might be improving different aspects of the hazard analysis or the damage analysis or the consequence analysis within the broader regional seismic risk assessment framework. And this is something that we're very interested in exploring, and it's sort of a continuation of Prateesh Kakoti's PhD research that's currently ongoing. So even though this work is not advanced enough to fully assess, what worked and what didn't, it really is clear that the SimCenter tools are really offering great versatility to explore these types of multi-fidelity regional seismic risk assessments. In particular, if you compare them to other platforms that, in my opinion, don't have that much versatility. But some of the anticipated challenges that we have is that it could be potentially difficult to incorporate seismic hazard data if you're working outside of the US. And actually, this issue has already been partly alleviated thanks to the connection to OpenQuake. And Adam actually alluded to this in his slide. So you can actually leverage OpenQuake seismic hazard analysis as inputs to an R2D assessment framework. I think another key challenge is that the use of multi-fidelity assessments really gives you results that are oftentimes not compatible. So if you follow, say, the low fidelity approach and then a high fidelity approach, and in part that is because the assumptions behind the risk metrics are not always consistent. So if you try to estimate recovery time, let's say using a conventional regional risk assessment and then using tools like ATC 138 or TREDS, you might get vastly different answers that are sometimes a little bit challenging to reconcile if you want to use the results collectively. And while this research is still ongoing, I do want to point out that some of my students have already explored some of the aspects of this work, maybe just focusing on the hazard component or doing this at a lower scale. And an example would be, again, work that Prateesh Kakoti did, where he tried to develop spectral acceleration Bayesian amplification factors, which could be applied to ground motion models to better capture, these amplification effects. And this could have potentially, been used to improve regional risk assessments, even if you're using that kind of conventional low fidelity approach, because you can use these factors to amplify the estimates of spectral acceleration derived from ground motion models. Another study that a former student carried out, and Kristen was also involved in this work, was exploring the post-earthquake functionality and surge capacity of hospital emergency departments. And I wanted to point this one out because, in a way, it's using this notion of multi-fidelity regional risk assessments, because we used a low fidelity type of model to estimate casualties in the region to get a sense of hospital demand, and then high fidelity models to understand the hospital capacity, right? So how did the hospital building structure respond? What kind of damage did it incur? And how did that impact the ability of the hospital to then treat the patients that were incoming? And you have links to these studies in the bottom right of the slide. Okay, the last thing that I wanted to touch upon is teaching and how SimCenter tools could also have a positive impact in the classroom. So looking back, it was in 2020 when I started integrating these tools into my graduate course. It's titled Civil 506, Performance-Based Earthquake Engineering. And the idea was to give students a hands-on assignment focused on a real application of the concepts that we cover in class, which oftentimes could be challenging, right? If you're talking about performance-based earthquake engineering as an overall framework. And in particular, students throughout the course work with OpenSea SPI, Pelicun, and TREDS. And I think the main benefit is that the students in the course really get exposed to open source tools that otherwise they don't encounter in other courses. And it's certainly a steep learning curve, but this is mitigated by the availability of tools like the PBE tool, which can give you a nice user interface if you're not comfortable, jumping into the Pelicun code directly. And I guess I must admit that it's also alleviated by having really good TAs, right, which are willing to work with your students to really help them understand what it is that they need to do and how to piece everything together. And in general, the student feedback that I've received has been quite positive, and I think they do find the experience challenging, but at the same time, it's quite rewarding for them. And in many cases, students then use these tools as part of their research. If they were doing a thesis-based master's, then they implemented that in their work, and then were able to publish some papers, which was great for them. The last thing I wanted to mention before we now transition to the Q&A is really to acknowledge that all of this is, collaborative in nature. And I actually want to thank the SimCenter team for their continued support and availability, which really has been instrumental to then make a lot of these projects that I talked about a reality. And I think I want to encourage everyone on the call, if you have ideas for improving or building upon the tools that Adam talked about earlier, I really encourage you to just reach out to the SimCenter team, because they're always willing to help and they're open to collaboration and new perspectives. And I'm sure many others on the call would feel the same way, in particular if they've already worked with the SimCenter. So with that, it looks like it's 10 o'clock. So this is, perfect time to sort of transition to the Q&A, and I'd be very happy to take questions if you have any.
All right. Well, thank you, Carlos. That was really great. Super inspiring. As you noticed, all this is kind of a work in progress, but that's partly what makes it fun, but also challenging at the same time, right? Keeping up with tools and so forth. This will conclude the recorded portion of our talks.